Good afternoon, everyone. I'm Mark Lewis, the Executive Director of NDIA's Emerging Technologies Institute. And I want to thank you all, first of all, for your support of NDIA and what we're doing at the Emerging Technologies Institute, and also for joining us for today's webinar, which is Hypersonics 101. So let me offer a few administrative remarks before we get started. First, all of our attendees are muted. If you do have a question during the webinar, you can submit your question to the question box on the webinar panel that'll be on the right side of your screen. And we will do our best to get through all the questions, depending on how many questions we have, no guarantees, but we will try our best. We're recording today's webinar. That'll be for NDIA, WID, WID, and NTSA members who are unable to attend, and frankly, for any member who wishes to review the material at a later date. And then within the next few days, we'll post the recording, our slides, and the answers to the questions to NDIA Connect for your review. So this webinar is the very first in a series that we're very excited to bring to you. We're calling it Tech Thursdays. And the idea is to distill some complex technologies into some introductory webinars aimed at laymen, people who aren't necessarily familiar. You might have heard the term, you might have heard the phrase, you're wondering what something is all about. What is it, a buzzword? What's the hoopla? Why is it important? We're going to be covering various topics in the science and defense sector. This series is frankly came about because we had feedback from our members at NDIA saying that you thought an educational series of this type would be of value to you. And I want to give credit to several of my colleagues, including Arun Seraphin, my colleague, Deputy Director here at ETI, Camilla Shanley, who runs most of ETI and is kind of the guiding force behind assembling this series. They put this together, and we hope it meets the needs and is responsive to what you've asked for. I want to emphasize this is our first attempt at one of these seminars. So we would really value your feedback and your thoughts. Let us know if we've targeted at the right level, too simplistic, too complicated. Let us know if it's valuable, if you have suggestions for future topics. At the end of the webinar, I'll tell you some of our planned future presentations, but other topics of interest, we'd be interested in hearing that. And also suggestions for future speakers for other events. Remember, as always, our goal here is to educate our NDIA membership and introduce new topics. And we're not here to sell any programs. We're not here to push any policy, no company products. We just want to educate and fill you in on why certain technical topics are important. So without further ado, let's dive into Hypersonics 101. And as I think some of you listening may know, hypersonics is my own primary area of research investigation. So I'm exercising the executive director's prerogative as we cover the subject. All right, so let's begin. Very first slide. All right, what is hypersonics? And for those of you who are completely unfamiliar with the term, I'd explain that we can divide various regimes of flight by several different parameters, but one of them is obviously speed, right? How fast does an airplane fly? A typical jetliner, typical commercial airplane, is flying less than the speed of sound, what we call subsonic. The speed of sound is given the term Mach 1. Mach number is your speed divided by the speed of sound. That's not just an affectation, by the way. There's real physics associated with the fact that you're flying less than the speed of sound or at the speed of sound or greater than the speed of sound. So subsonic is less than the speed of sound. A good example is a Boeing 787 traveling at about 600 miles per hour. Sonic is the speed of sound, roughly 680 miles per hour. The first airplane to break the sound barrier, as it was called, it wasn't much of a barrier, was the Bell X-1 in 1947. And if you're flying at that speed, you're considered to be sonic. If you're in the vicinity of the speed of sound, you're considered to be transonic. Flying fast than the speed of sound, you're at supersonic speeds, Mach numbers greater than 1. Good example is a fighter jet. F-15 can travel at 1,650 miles per hour, a supersonic airplane. Hypersonic refers to flight in excess of about 5 times the speed of sound. Now, important point. When a vehicle transitions from subsonic to supersonic through the speed of sound, the physics of the airflow changes, and it changes fundamentally. Right? When you go faster than the speed of sound, you have new phenomena associated with flight. For example, you form a shock wave in front of the vehicle. That's a sudden change in pressure and temperature. We don't see those when you're flying at low speed, unless you have a local supersonic region on the airplane. Now, what about when you go from supersonic to hypersonic? There's no sudden change in physics. There's no dramatic variation, flow doesn't change color from green to red, nothing like that. And as a result, the transition from supersonic to hypersonic is really more of a guideline. It's more of a rule of thumb than driven by actual physics. But there are a number of phenomena associated with hypersonic speeds such that we put it into a separate category. All right. So coming back, there is no fixed definition of hypersonics. If I got 10 hypersonic experts in the room, I might have 11 different definitions of hypersonics. But in general parlance, we say it's flight in excess of about 5 or so times the speed of sound. Some people might say 6, some people might say 4. That's the usual guideline. I mentioned that at any supersonic speed, you create this sudden jump in pressure and temperature, this shock wave. At hypersonic speeds, those shock waves get pressed very, very closely around the vehicle. Right? When I'm traveling at near the speed of sound, slightly higher than the speed of sound, I generate a shock wave, but that shock wave is separated from, can be standing off from the vehicle. Not so at hypersonic speeds. It's pressed very close to the surface of the vehicle. Heating becomes really significant. You're traveling so fast that surfaces get hot due to friction. Also leading edges, because you've got air hitting those leading edges. So that's delivering kinetic energy. Energy of the gas is being deposited at the front of the vehicle, on the edges of the vehicle. And so those parts become really hot. Also, whenever we look at flow over a vehicle, we ask the question, is the flow smooth and laminar, or is it turbulent? And the transition from laminar to turbulent is something that's been extremely well studied, very well understood at lower speeds, not so much at high speed. When we undergo this transition, it can change the drag, the resistance motion through the air, but it can also change the heating rate. So that's an important parameter as well. In any aerodynamic system, any airplane, we worry about a region of flow right by the surface. It's called the boundary layer. The boundary layer is the part of the flow where skin friction is most important and heating can be most important. One of the defining features of hypersonic flight is those boundary layer effects can be significantly different than at lower speeds. Boundary layers can get really thick and their properties can change compared to a lower speed flight. And then finally, because those temperatures can be so hot, we can start to see chemistry of the air. So oxygen molecules in the air can start breaking apart. Ultimately, nitrogen molecules can start breaking apart. And if we get to really high Mach numbers, say in excess of about Mach 9 or Mach 10, then we'll start ripping electrons off of atoms. We get ionization effects. We get charged particles in the flow. And that not only affects the heating on the surfaces, but it can also have other impact. For example, your ability to communicate with radio waves through that shock layer can be attenuated if you have plasma effects. All right. So the question: how hot is heating rate significant? Well, it really depends on the shape of the vehicle. All right. A good rule of thumb is the sharper the leading edge, the hotter it becomes. The heating rate, the rate at which energy is deposited to the leading edge, scales inversely with the square root of the radius of curvature. So sharper is hotter. And for most of the hypersonic applications we look at, we're talking about many thousands of degrees of temperature. And that's pushing the limits of most of the high temperature materials in some cases that we would envision using. All right, so let's step back. Why would we want to do this? Why would we want to fly at hypersonic speeds? Many, many applications. From a Department of Defense standpoint, I will posit that hypersonics represents a combination of several factors. It's not just speed, although that's the defining parameter, but it's the combination of speed and maneuverability in the atmosphere. Because a hypersonic vehicle is flying in the atmosphere, so it's that maneuverability. And it's also the altitude at which these vehicles can operate. That makes them more survivable. It means they're difficult to detect, they're harder to track, their purpose can be ambiguous. And because of all that, that also means they're difficult to stop, not impossible to stop. But if I, for example, build a hypersonic cruise missile, it's going to be more difficult to identify, find, fix, track, target, and eventually stop than, say, a lower speed counterpart. A hypersonic medium range missile, for example, is going to be more maneuverable than its ballistic counterpart. That means it's going to be less predictable. It can be very unpredictable, in fact, and they're once again harder to stop. Hypersonics can be useful if I've got to do a rapid response against a time-sensitive target, because it reduces the time to target. Hypersonics can offer precision strike alternatives that today might only reside with a nuclear option, which obviously should always be the option of last resort. You can think of a range of targets, say deep in an enemy territory, that today we can only hit with a nuclear strike, something we wouldn't want to resort to again, and that we might be able to strike with a precision surgical strike using a hypersonic system. Hypersonics also gets inside of what in the DoD referred to as the OODA loop: observe, orient, decide, and act. It's the way we take action in the DoD. And if you're moving fast, if you're unpredictable, if you're hard to identify, it makes it difficult for an opponent to decide what you are, where you are, what you're attempting to do, and how to respond. And that's what hypersonics is all about. It's increasing the speed of action to make it more difficult for an opponent to counter and reduce your mission effectiveness. All right, so two basic approaches to hypersonics. Right, the first, and you'll hear a lot about this in published material, in recent program descriptions. First is what we call air breathing. Air breathing simply means that the hypersonic vehicle is flying through the atmosphere and has an inlet, basically a hole in the front, where air comes in, and the oxygen in the air is used to burn with the fuel. It's the way all jet airplanes work. It's actually the way human beings work, by the way. We're air breathing. We use oxygen from the atmosphere to burn with our fuel to metabolize our food, right? It's a very efficient way to operate because you're not carrying the oxidized component of your combustion system. You know, why carry oxygen with you when you're surrounded by it? Now, the other approach to hypersonic speeds is to use a rocket. Rockets can accelerate very quickly, can get you to high speed. And for most of the hypersonic systems that you'll hear discussed, we talk about rocket boost glide systems, where you've got a hypersonic glider that is accelerated up to speed, up to some high Mach number, and then the glider separates from the rocket and cruises back down without power. Both of these technologies have different applications. They have different values. Air breathers are really good for cruising for long distances efficiently in the atmosphere. They tend to package better. You can make them smaller for a given mission because you're not carrying oxygen on board. Rocket boost glide systems can go further. They can actually be more maneuverable. And they also have the advantage that rockets are relatively simple. We know how to build rockets. We've been doing this for decades. Whereas air breathing systems require a little bit more technological investment because the engines that would power us on an air breathing system are a little bit more complicated. All right, so why would you want to breathe air? Why would you want to have an inlet, a hole in the front, and an engine that burns oxygen from the atmosphere? This is a curve that's generally attributed to a legendary name in hypersonics, a gentleman by the name of Tom Curran, who worked at the Air Force Research Lab for many years. And in the mid-1980s, Tom Curran put together this curve which captures the performance of various propulsion systems. And the metric of performance is something called specific impulse. Specific impulse is defined as the thrust of an engine divided by the rate at which the engine is consuming fuel, measured as a weight, not a mass. So specific impulse is basically bang for the buck. It's how much thrust I get for an amount of fuel that I'm burning. And you see plotted on here that the general trend is that air-breathing engines give you a higher specific impulse the lower the Mach number. So for example, a turbofan engine can give you specific impulses in excess of 7,000, 8,000 seconds. Units of specific impulses work out in seconds. As you start marching up the Mach number curve, specific impulse gets lower and lower. When you get to a type of engine known as a ramjet, which is a very simple engine, it's just an empty duct, you get specific impulses in the neighborhood of 2,000 seconds. The engine that we view as the engine of choice for air-breathing hypersonics is something called a scramjet engine. That stands for supersonic combustion ramjet, and that'll get specific impulses in the neighborhood, we believe, of about 1,000 seconds. Compare that to a rocket. So you see in that curve, the rockets are shown at the bottom of the curve. The best rockets that we can build have specific impulses of about 460 seconds. So the rockets are basically delivering about half the specific impulse as compared to an air-breathing engine. Why is that? Well, for a simple reason, that we calculate the fuel that's being consumed in the rocket. We have to calculate it based on both the fuel and an oxidizer that's carried on board the vehicle. Whereas for the scramjet engine, we're calculating the specific impulse based entirely on a fuel, but we're not carrying an oxygen. We're not carrying an oxidizer. That's coming in through the hole in the front. It's coming in through the inlet. So as a result, we're carrying less stuff to make the engine work. We're gathering stuff as we go along. That means we don't have the fuel, We don't have the fuel tank and the associated structure. So it's a more efficient way to plow through the atmosphere. All right, so with that in mind, let's talk about some of the concepts, some of the systems that would apply hypersonics. And this is kind of a whole range of various hypersonic vehicles. At the bottom of the slide, you see pictures of spacecraft. Any spacecraft that enters from the atmosphere back to Earth is probably traveling at hypersonic speeds. That includes the Apollo capsule, the space shuttle, anything that enters a planetary atmosphere, say the Mars probes that we've flown. But if you notice, those spacecraft are designed with really, really thick, blunt shapes. That's to handle the heating on re-entry. Right? Someone asked the question already about how hot is hot for hypersonic shapes, and I pointed out the sharper you are, the hotter you get. So one way to avoid getting too hot is you have a thick, blunt shape, big rounded shape, and that controls your heating. Unfortunately, that also introduces lots of resistance to motion, drag. You've got a big, thick, blunt shape. You've got a lot of resistance as you move through the atmosphere. For a spacecraft, that's not a problem. If I'm a space shuttle coming back from orbit, I want to slow down. If I'm an Apollo capsule coming back from the moon, I want to slow down. So I'm both handling the heating rate, but also providing high drag, which is part of the mission. On the other hand, if I want to build a weapon that's traveling at high speed through the atmosphere for a long period of time, I don't want to slow down. I don't want lots of drag, so I don't want to be blunt. I want to be sharp. And so I adopt an entirely different design. I want to go towards a very slender, sharp leading edge configuration, and that's why some of these heating rates become important. All right, so at the top of the slide, you see a couple of concepts for these sorts of slender hypersonic shapes. Far left-hand side, you see various weapons concepts. That includes rocket boost glide, like the conventional prompt strike system. That's similar to systems that are being developed today by the US Army and the US Navy. At the top, you see an air-breathing cruise missile concept. That's a picture of the X-51, but that's the progenitor to a couple of programs underway right now, most especially under the DARPA Hawk program. Includes an air-breathing system. Air-breathing systems being developed by Lockheed Martin and by Raytheon, as well as a program called Hi-Fly 2 that the Boeing Corporation is developing. Those are all powered by supersonic combustion ramjet air-breathing engines. Moving further along, you can imagine hypersonic aircraft. Again, they'd be slender, powered by, at some phase of their flight, a scramjet engine that might do a surveillance mission, it could do a reconnaissance mission, it could be a deep penetration airplane, it could be manned or it could be unmanned. And then finally, kind of what I call the brass ring of hypersonics is to use hypersonics to get all the way up to orbit. In other words, instead of flying to orbit with a rocket, you fly up to orbit as an airplane. And there are many advantages if you could do that. It's much easier to get an airplane ready for flight than it is to get a rocket ready to fly. It's much easier for it to be reusable as well. So you'd imagine that reducing the cost and easing the access to space. The problem is the technology to do such an air-breathing launch system is not quite at hand. It's a long way off. So it would, at this point, probably require at least 1 or 2 miracles. That's our far future. It's not our immediate future. All right, so let me go back to the idea of propulsion. If I'm designing a hypersonic vehicle, I've got a couple of options. I've already mentioned a few. One is rockets. We know how to build them. We've been building them since the days of Robert Goddard out on a field in Massachusetts. Ramjets, which are very simple engines. We've been flying vehicles powered by ramjets, can almost get you to hypersonic speeds. Not quite. They're supersonic engines. They start to run out of thrust as you approach the hypersonic speed range, and I'll explain that in a minute. So with that being said, there's an alternate approach that we call a scramjet, a supersonic combustion ramjet, which in its simplest form is really just a ramjet in which the air moves through the engine at very, very high speeds. In other words, the air remains at supersonic speeds, hence the name supersonic combustion ramjet. And there are all sorts of other engines we might consider, including what are called combined cycle engines, where we match a conventional turbofan or turbojet to a ramjet and a scramjet. And we would do that because scramjets are probably only good for hypersonic speeds if you want to build something like an airplane that can take off from the ground, that can operate, can taxi along a runway, that can accelerate from almost a stop and fly through various speed ranges. You have to have some other type of engine that can do that. Liquid air cycle engines, that's a whole different approach to high speed, but also a really exciting one. That's where you basically use a very cold fuel, maybe a cryogenic liquid hydrogen fuel or a liquid methane fuel. and you condense air. So air comes into an inlet, you make it really cold, you liquefy it, and now you've got liquid oxygen available because you've cooled it down with your air. You can burn that liquid oxygen very much in a conventional engine, maybe in a conventional rocket engine. And then there are other propulsion concepts that have been proposed over the decades, including using some form of plasmas to somehow enhance the operation of an engine, maybe enhance combustion, or do something where you use plasma effects to steal energy from the flow and deposit the energy back later on in the flow. Lots of different engine cycles you could imagine. In terms of fuels, what fuels work for hypersonics? Well, you can go with a really cold fuel. Hydrogen was often posited as the fuel of choice for hypersonic flight. Hydrogen gives you lots and lots of energy for an amount of mass that you burn. But it has a downside. It has to be stored as a very, very cold liquid. And it's not a very dense liquid. So if you fill a tank of gas with hydrogen, right, that tank's got to be really large for the amount of mass that you put inside. So it adds to the weight of the structure. Conventional hydrocarbons, right? We've had high-speed airplanes that flew powered by hydrocarbon fuels similar to jet fuels. The SR-71 spy plane flew at about 3.5 times the speed of sound on a jet fuel known as JP-7. Those have a lot of advantages. Hydrocarbons have reasonable energy per unit mass, but they have a higher storage density than those cryogens, so they have some packaging advantages. Endothermic fuel. So endothermic means you absorb energy. That's key in some hypersonic applications because you want fuels that can suck in heat from the engine to kind of recuperate that heat so you don't lose that heat. Say heat that's deposited in the walls, it keeps the walls of the engines from melting, and then release that energy again when the fuel burns. So it becomes a very efficient fuel. That was an approach taken on the X-51 program that the Air Force Research Lab pursued, and also an approach that the DARPA Hawk program has been taking. Fuels that can soak in heat and then release that when the fuel is burned inside the engine. And then, of course, there are always crazy ideas, different fuels we might imagine. There have been proposals for nuclear-powered ramjet engines. Turns out to be a really bad idea, by the way, if you worry about radiation issues. But various other engines that have been proposed over the years for hypersonic systems. All right, so let's talk a little bit about programmatics and history. The great aviation historian Dick Hallion has shown that hypersonics has tended to follow a 15-year cycle. It's a boom and bust cycle. And that's been unfortunate because it means that we've gone through this series of starts and stops throughout the history of hypersonics. The first hypersonic program, the first hypersonic vehicle, man-made system, was something called Project Bumper that was flown in the late 1940s. It was basically a sounding rocket that was launched on top of a captured German V-2 rocket. And that kind of began the hypersonic era. And then after that, basically every intercontinental ballistic missile that was built really was a hypersonic system because they flew in Mach numbers well in excess of Mach 5. In the mid-1960s, there were a variety of programs. I mentioned the Air Force had a program called the Aerospace Plane, not to be confused with the later National Aerospace Plane. There was a program called ASSET. Air Force and NASA flew something called the X-15 rocket plane, which is an amazing experimental airplane that flew throughout the 1960s. And then the 1970s come along and the funding kind of drops out. The 1980s, especially the mid-1980s, saw the resurgence of hypersonics with a program called the National Aerospace Plane, the X-30. President Ronald Reagan went on national television. He announced this as a national effort, involved DARPA, it involved the Air Force. There was a government contractor team put together. Very, very exciting time. This plan was to build a single stage to orbit airplane that could take off for a long runway and fly all the way up to orbit. In retrospect, it was a bridge much too far. It would have required technology that we really didn't know how to build, but it really ignited this excitement about hypersonics. And then after the NASA program ended, after we realized it was a bit of a technological challenge, you saw once again a decline in funding in hypersonics going into the early 2000s. You saw a resurgence in hypersonics. NASA had a program called X-43. It was a subscale hypersonic demonstrator. The Air Force had the X-51 that I mentioned previously. You saw the conventional Prom Strike rocket-boosted programs, including programs with the Navy, Army, and DARPA. And then you saw the reduction in funding until we get to the current era. And right now, hypersonics is doing extremely well. I would argue that it would require a whole seminar to explain why that is, but suffice it to say, I think there's been a general recognition of the importance of hypersonics, and also there's been a recognition that we have peer competitors, especially Russia and China, that have built on our investments. They've seen our work, they've taken our research, and they're moving very, very quickly. And by many metrics, you could argue that both Russia and China have now surpassed our capabilities. Building on that theme, a couple of milestones in hypersonic flight. I already mentioned in 1948, the far left-hand side is that Project Bumper, which was a sounding rocket put on top of a V-2 rocket. The gentleman standing in front of that rocket is a legendary figure in aerospace engineering named Frank Molina, Texas A&M graduate, who headed Project Bumper. Next to that, you see the X-15 rocket plane. It still holds the record for the fastest human piloted aircraft in the atmosphere, Mach 6.7. It was flown by astronaut by pilot Pete Knight, unfortunately, that record still stands. We haven't beat it. Other milestones in hypersonic flight: the Galileo space probe that NASA dropped into the atmosphere of Jupiter is the fastest hypersonic man-made object that we've flown. Entered the atmosphere of Jupiter at about 65 times the speed of sound. I'll contrast that in the lower right-hand side. The fastest hypersonic vehicle that has entered Earth's atmosphere was the Stardust space probe. It captured some material from a comet, and that entered the atmosphere at about 43 times the speed of sound, Mach 43. Fastest human flight, fastest manned entry into the atmosphere was actually the Apollo 10 capsule, and that was Mach 37 times the speed of sound. So bottom line is, we have been flying at hypersonic speeds for quite some time. The field isn't new. What is new is this focus on maneuverable vehicles, on air-breathing vehicles, and also the interest in defense applications. All right, so building a little bit on that theme, I mentioned the National Aerospace plane, the X-30, and this is going to show you why hypersonics is so challenging and some of the challenges that we faced. When the National Aerospace plane program was first proposed in 1986, it was conceived as an airplane that would fly up to about 25 times the speed of sound. That's the speed you need to be in order to reach orbit. It was going to weigh in at about 50,000 pounds. By the time the program was canceled in 1993, it wasn't going to make it up to Mach 25. In fact, this design, in aerospace parlance, did not close. The design wouldn't reach Mach 25. But more importantly, the vehicle got larger and larger. It had grown to 450,000 pounds, almost 500,000 pounds of vehicle. And a good rule of thumb in aerospace engineering is that weight is cost. The heavier your vehicle, the more expensive your vehicle. And indeed, this vehicle would have been extremely, extremely expensive. And so the program ultimately wound up being canceled. Now, what were the challenges? This is an eye chart. All right, this is not going to be on the exam, but this is intended to show you all of the design challenges that you face when you try to design one of these hypersonic vehicles. Right? Everything from designing the engine, integrating the engine so it fits well with the airframe. Because these vehicles are so slender, the whole front of the vehicle becomes part of the inlet system. The whole back of the vehicle becomes part of the nozzle. So anything you do to the front of the airplane is going to affect the way the engine operates. Anything the way you do to the engine is going to affect the way air flows over the back of the vehicle and the aerodynamics. So very, very challenging. Modeling what goes on at the leading edges is difficult. Modeling what goes on in the airflow right on the surface of the vehicle, very difficult. Understanding what goes on inside the engine, once again, really, really difficult. I like to say that hypersonic vehicles are the most tightly coupled vehicles of any aerospace system that I know. You cannot design any part of a hypersonic vehicle separately from the rest of the craft, right? The engine is part of the airframe. The airframe is part of the engine, right? These really are self-propelled fuel tanks, right? And that makes the design challenges very, very, very daunting indeed. There are ways around this though, and I'm gonna show you one design concept right here, which is called a Hypersonic Waverider. I love the Waverider concept because it's a very, very elegant aerodynamic concept. And in the Waverider concept, you basically start by picking the shock wave, deciding what the shock wave will look like that would be wrapped around the vehicle. And then you find the vehicle shape that gives you that shock wave. So unlike with most aircraft designs, where design the aircraft and then figure out what the airflow is going to look like around the aircraft, with the Waverider, First, you design the airflow, and then you find the shape that gives you that airflow. It's not a new idea. It was introduced by Scottish researcher Terry Nunweiler back in the late 1950s. It was really developed beautifully at the University of Oklahoma by Maury Rasmussen, and others jumped in. Kevin Bocut of Boeing Corporation has done a tremendous amount of work on the Waverider concept, explored extensively through the 90s and the 2000s, and it's become the basis of generation for almost all of our modern concepts for engine airframe integrated hypersonic systems, including the X-51 vehicle and then some subsequent designs. All right, so let's talk a little bit on the history of propulsion. I mentioned the scramjet engine. Let's talk about why that's important. The scramjet engine is a really simple engine concept in basic principle. It's really just an open tube, air comes in, fuel is injected, it gets heated and expands out the back. It's an idea that dates back to the 1950s. In the late 1950s, two researchers at what was then the NASA Lewis Research Center, actually it predates NASA, it was run by the National Advisory Committee for Aeronautics that became NASA. They wrote a technical note in which they had done this thought experiment. In a typical ramjet engine, air comes in the front and it slows down. And I'll explain in a few minutes why it slows down. And fuel is injected, it mixes, it burns, and then that air expands out the back. And these two researchers, Weber and McKay, did the thought experiment. What if we didn't slow the air down? What if we kept the air moving at high speed? How would that change the engine? And so they came up with this idea for a scramjet engine that could power past the limits of a ramjet. And what they concluded that was that when you went to the higher Mach numbers, in excess of about Mach 6 or so, that they could get thrust greater than drag, and this high-speed scramjet cycle was indeed the preferred cycle. That was conclusively proven 46 years after they theorized this engine concept. And that was when NASA flew the X-43 vehicle. All right, so to explain in a little bit more detail, these are different air-breathing engine types. On the top, you see a jet engine. Air comes into the front of the jet engine and gets compressed by a series of blades in what is called the compressor. That high-pressure air feeds into a combustor. Fuel is injected. It mixes. It burns. That makes that mixture hot. That hot mixture then accelerates through nozzles through a turbine. That turbine consists of blades that then get spun by the moving air. Those blades run the compressor at the front of the engine, and the stuff that all comes out the back gives you thrust. Jet engines stop working, about Mach 2.5 or so. They start to become less and less efficient. Above those Mach numbers, you want to go with a ramjet. And in a ramjet, air comes in the front, but instead of a mechanical compressor with blades, you just have an inlet that slows the air down, that increases the pressure, so that again, the air can go into the combustor, fuel is mixed, it burns, it heats up, and expands out through a nozzle. I like to think of the ramjet as a jet engine where I've just tossed out the compressor and the turbine. I don't need the compressor to compress the air because I'm compressing it by flying into it. And I don't need the turbine because I don't have a compressor, right? So a ramjet is a very simple type of engine. But the key in a ramjet is I'm still slowing the air down. And I do that for two reasons. One, it's more efficient to heat air when it's slower. It's a basic principle of thermodynamics that when the air is moving faster and you burn the fuel, you lose some of the energy to what is called entropy. Right? You take a loss in energy. It's not recoverable. So I want the air to be moving more slowly through the engine. So more of the energy of the fuel gives me useful thrust. The other thing, of course, is when the air is moving slowly through the engine, it gives me more time to inject the fuel and to have it mixed efficiently and to burn. And related to that, it's much easier to inject fuel into a lower speed flow than into a higher speed flow. Now, in contrast, in a scramjet, I keep the air moving at very high speed. That introduces some inefficiencies in the combustor. I'm adding energy to a high speed flow, so some of that energy gets lost. I also have less residence time. There's less time for the air to sit inside the engine. So that means I have less time to inject the fuel, to mix it, and to burn it. So that's on the downside. But on the upside, my inlet can actually be more efficient, because in a ramjet, when you slow the air down, you generally form a strong shock wave. Shock waves give you losses. You lose energy in a shock wave. Scramjets also have shock waves, but they're much smaller losses. They're weaker shock waves. So the advantage goes to the scramjet once you get into the Mach 5 range, once you get into the hypersonic range. Here's a chart that also captures that. So what I've shown here is termed the classic ramjet curve, and this is the thrust that you generate from a ramjet divided by the rate at which fuel is being consumed. It's that specific impulse term that I referred to earlier. It's the bang for the buck. And what you note is that a ramjet cannot produce thrust at very low Mach number. At Mach number 0, there's no thrust. Why? Because remember, the ramjet is compressing the air by ramming into it, by moving into it. If you're not moving, you're not compressing the air, so you can't produce thrust. As the ramjet climbs up the Mach scale, you get more and more compression, thrust goes up, specific impulse goes up, until you get to some point, which is sort of a peak Mach number, usually in the 2.5 range for hydrocarbon fuels. And then as you continue to increase your Mach number, the thrust falls off again. Why is that? Remember, in the ramjet, air is coming in and slowing down. When it slows down, you're conserving energy. So relative to the engine, that air is getting hot. The temperature is going up. At some point, you reach a temperature such that the air has slowed down. Temperature gets so high, it is above the combustion temperature. When you squirt fuel into a really hot air, it doesn't burn. It can't burn. The gas temperature is too high. If you can't burn the fuel, you can't release energy. You don't get positive thrust. So as a result, ramjets begin losing thrust when you get to the hypersonic range. By the time you get to Mach 6 or so, a ramjet cannot produce thrust because that slow down air is hotter than any combustion temperature inside the combustor. And that's why you do a scramjet. And I've shown the dashed line for a scramjet curve where the scramjet can continue to produce thrust for the very simple reason that you're never fully slowing down the gas. It's moving at high speed through the engine. So the gas never reaches that equilibrium combustion temperature and therefore can produce thrust right up the scale. And that's what produces this chart that we saw earlier. All right, so a little bit back to a little bit of history. First scramjet flights, NASA flew the X-43 in 2004. X-43 was an amazing program. It was a subscale vehicle, joint effort between NASA Langley, then NASA Dryden, now NASA Armstrong, with work from other NASA centers. It was based on a vehicle concept that was developed by NASA Langley. It was powered by a scramjet engine that could operate on hydrogen fuel. There were 2 successful flights of X-43. Both of those flights lasted in excess of about 10 seconds. At the end of those flights, those vehicles crashed in the Pacific Ocean, so they were not recovered. But for those 10 seconds, those vehicles proved beyond any reasonable doubt that scramjets worked, that you could operate a vehicle on an air-breathing engine in the atmosphere at hypersonic speeds. And then, following that, in the 2010 to 2013 timeframe, U.S. Air Force built and flew the X-51 program with support from DARPA. The big difference between X-51 and X-43 is X-51 was a lower Mach number vehicle, but it was powered by hydrocarbon fuel, JP7, the same jet fuel that powered the SR-71 spy plane. And whereas the X-43 flew for 11 seconds or so, X-51 flew for upwards of 200 plus seconds, right? So long duration flight. In fact, for the last flight of X-51 that occurred in 2013, that vehicle could have flown longer if it had more fuel on board. And the secret to doing that, the engine of X-51 was actively cooled. There was fuel circulating through the walls of the engine, and then that heated fuel was what dumped into the combustor. And so the engine was cooling itself. It could handle the heat loads of high temperature. It was in equilibrium, and so it could operate almost indefinitely. And more recently, just this fall, and then again just a few weeks ago, the DARPA Hawk program had 2 successful flights building on that legacy of scramjet-powered systems. Really exciting, getting us back into the air-breathing propulsion game. All right, so let me kind of go back to that National Aerospace Plane Program. In 1986, when that program first kicked off, there was a whole long list of things we didn't know. We didn't know if you could build a scramjet, let alone operate it, at any Mach number, all the way up to orbital speeds, which was the goal of the X-30 program. We didn't know if an engine flying at high speeds could do what's called an unstart, which is where you spit out a normal shock wave, a strong shock wave. It happens in supersonic airplanes. We didn't know what would happen with a hypersonic airplane. We didn't know if you could inject fuel and get a combustor to work. We didn't know if leading edges could handle the heats. We didn't know what the boundary layers would look like, the flow right by the surface of the vehicle. We didn't know if you could design an inlet for an engine that could handle distortions and that those inlets could be efficient. We didn't know if you can control a hypersonic vehicle. We didn't know if you could even design it so it had very high lift, but very low drag. We didn't even know what the inlets should look like. Right now, 2002, we've answered most of these questions. It's really an exciting time for hypersonics. We've flown scramjets up to Mach 10. The X-43 did that. And we've done steady state in the Mach 5, 6 range, right? We know that we can survive engine unstarts. We've done fuel injection. Scramjets work. We've got leading edges that have survived the heating rates. We've learned a lot, not entirely, but we've learned a lot about boundary layers and when they go from smooth and laminar to turbulent, although there's a lot more to do. We've controlled these vehicles. We've designed them with very efficient lift over drag ratios, very efficient aerodynamic shapes. And we've done a lot of work on inlet design. If you look at the inlet, say, of that Hawk vehicle that I just showed you, it's very much more sophisticated, frankly, than the inlets that we flew on either X-43 or X-51. We have learned a lot. So let me ask, where do we go from here? All right, what are the next steps? And then this is my penultimate slide, and we'll open this up for questions. All right, first, as I indicated, there's a lot of activity right now in the Department of Defense, a lot of effort being put into hypersonics, but frankly, the low-hanging fruit being weapons applications. And that includes both rocket boost flight systems, but also air-breathing systems as well. The General Accounting Office last year wrote a report on Department of Defense programs and came up with no fewer than 70 programs in the Department of Defense. Funding is flowing very effectively. Each of the services is fully engaged in hypersonics. The Army, the Navy, the Air Force, DARPA has a robust program in hypersonics, and the Office of the Undersecretary of Defense for Research and Engineering under Heidi Shyu is pursuing a very aggressive program in hypersonics, including a joint hypersonic transition office that is working hand in glove with the U.S. Navy, Naval Surface Warfare Center at Crane, which has become the field office that's overseeing some of the transition activities. And there's even this great hypersonic university consortium that was started by the Joint Hypersonic Transition Office that has 90 universities involved with various aspects of the department's activities. So bottom line, there is a lot going on today in hypersonics. So what do we do? Well, first, clearly we need to continue hypersonics at scale. By scale, I mean moving away from demonstration programs and experimental programs and moving to the delivery of real weapons and real capabilities. After that, reusable systems. You know, early on, I talked about aircraft, unmanned or manned, combined cycle systems where you can take off on a jet engine and then accelerate to hypersonic speeds, things that can do intelligence, surveillance, reconnaissance, all right? Continue to look at alternative propulsion flow paths. A lot of interest now in spinning off to commercial. There are companies that are stepping up. They want to do commercial hypersonic systems. That's really exciting. Anyone who's ever flown an airplane flight from the United States to Australia appreciates systems that use different combined cycles. So you might have a jet engine and a ramjet, a jet engine and a scramjet, all of which could allow you to expand your Mach scale. Oh, I think we've lost audio. Oh, yeah.
Audio is back.
Okay.
It's back, Mark. You're all good.
Okay, audio is back. Oh, all right. I'll just do very quickly the slide. I just wanted to show, for those of you who missed it, this is a combined cycle engine. And basically in a combined cycle engine, I realized that no single engine can operate across the entire Mach scale, right? A high Mach number engine cannot operate at low Mach numbers. So I need some combination of engines, maybe a single engine that can change its shape or its operating mode, or several engines in combination to get me all the way, say, from Mach 0 to Mach 6. Oops. All right, I've already mentioned the General Accounting Office report, 70 DoD programs. everything from fundamental research at AFOSR to flight tests, the DARPA flight test, the conventional problem strike flight test, and I mentioned the university consortium. So the bottom line here is this is an amazing time to be working in hypersonics. There's tremendous interest, tremendous focus, really because of concern about foreign activities. And with that, I hope I left enough time for question and answer. And I already see some questions. So let me go to the questions that we received. The first question is, what do we know about hypersonic missiles Russia claims to have used in Ukraine? Great question. So we know a lot about those hypersonic missiles. The intelligence community has done a marvelous job of looking into what our peer competitors have been doing. I'm going to tell you that the Russian hypersonic systems, they tend to build on legacy investments that the Russians have made in the Cold War era. Honestly, I'm just going to give you my opinion. The Russian hypersonic systems don't really impress me that much. They don't scare me very much. What scares me most is the strategic communication that is associated with the Russians flying those systems. So, for example, why are the Russians even using hypersonics in their attack of the Ukraine? Normally, you would use hypersonics to penetrate against sophisticated enemy air defenses. They're not facing that. You might use it against time-sensitive targets. They don't seem to be facing that. You might use it against deeply buried targets. They don't seem to be facing that in Ukraine either. So I view this more as strategic messaging. This is Russia telling the United States, we've got it, you don't yet. We've already deployed it. And also remember, both the Russians and the Chinese have made their hypersonic systems ambiguous. The same systems can be both conventional or nuclear. So I think it's the Russians trying to introduce some element of doubt in our minds. So that's what that's all about. But, you know, I'll come back to it. Don't forget, this reminds us that the Russians have already deployed these weapons and we have not done so yet. Let's see. Someone's right. This is the first time I've heard that there's an upper limit of combustion temperatures. Yes. All right. So let me explain that. It's basic chemistry. All right. If I burn, say, a fuel in an oxidizer at a certain pressure, it will that combustion process is really a chemical reaction in which I've got components that are breaking apart and recombining in some way to produce products, and those products release energy. So, for example, the simplest combustion system I can think of, I burn hydrogen and oxygen. That produces water, and in the process of producing water, it releases heat. Now, in a hydrogen oxygen rocket, we use that heat that gets released to heat up the water. That becomes the mass that expands out the back of the nozzle. So the source of the energy, the reaction, is also the source of the mass that comes out the back of the engine. If you take water, I give you a flask of water, and you heat it up to really, really high temperatures, you will find that that water starts to break apart. You're putting in so much energy, and you're breaking the bonds that you formed between hydrogen and oxygen. You'll break it down to its components. You'll break it down into hydrogen and oxygen again, all right? So that puts a temperature limit on combustion for a given pressure. If you go above the equilibrium combustion temperature, you break apart the products of combustion back into their constituents, and that's an upper temperature limit. So that's what we're talking about when we talk about the limit on ramjets. All right, next question. Oh, it's not a question; it's a comment. Incredible. Well, thank you very much. You have impeccable taste. I thank you. Let's see. Other question? We fixed. Never mind. Audio is back. Okay. Is there any interest in looking at new navigation sensors or methods for hypersonic vehicles? The very simple answer is yes, absolutely. All right. That is essential in these systems. Right? A weapon is only useful if it hits its target. It's especially challenging if you're moving at high speeds, if you're maneuverable, right? Less reaction time. And so there really has been a fairly robust body of work done in hypersonic navigation, hypersonic maneuvering. I'll tell you that putting a seeker on a hypersonic vehicle, hypersonic weapon, is indeed technologically challenging. If you're moving at high speeds, the design of that seeker becomes a challenge. It's for reasons you can imagine. If you're looking through a window at a target, you've got to look through a boundary layer. If you're going at really high speeds, you can get high temperature effects that can create distortion effects due to the airflow moving over that window. But the bottom line is, yes, absolutely, navigation is important. I'll tell you, outside of hypersonics, You know, when I was in the Pentagon, we'd always ask the question, are our navigation systems vulnerable? We depend a lot on GPS in the Department of Defense, and the GPS constellation is vulnerable. And so looking for alternate navigation and guidance systems in hypersonics is absolutely key. Okay. All right, what about the Chinese capabilities? Great question. By any metric that I can come up with, China has exceeded our capabilities, right? China has basically taken all of our research. They've taken our open literature. In some cases, they have exfiltrated our closed information. They have begged, borrowed, and stolen, and they have invested a tremendous amount of money into hypersonics. They've invested into their universities. They've invested into infrastructure. They have built wind tunnels. They've invested into their government industry partnerships. They have been flying vehicles, test vehicles, at a phenomenal rate, at almost 10 times the rate at which we've been flying. And as a result, their success rate has been much higher than ours, right? If I look at our flight test rates, if I'm generous, I'd say we have about a 50% success rate of our experimental vehicles. The Chinese are in excess of about 80%. So really quite remarkable. And more importantly, they've actually gone to deployed systems. In 2019, China did a military parade, and they showed off their hypersonic weapons in their military parade. Now, I will tell you, someone asked earlier about Russia. I worry much more about China than I do about Russia. Because the things that worry me the most about China are the hypersonic weapons that they would use in the Pacific theater that could most effectively neutralize America's advantages. Right? Think about our advantages in that theater. It's our surface navy and it's our air power. China's hypersonic weapons, some of their weapons are specifically aimed at targeting our surface fleet, targeting our aircraft carriers, targeting our surface vessels, and targeting our airfields in that area. And that's a really scary proposition. You know, China doesn't need to have a world-class navy to go against our world-class navy if they can hold our navy at risk with hypersonic systems. They don't need to have a world-class air force to go against our world-class air force if they can crater our runways so our airplanes never get off the ground. So it's very clear from the China standpoint, hypersonics is a very credible, rational investment for them and something that they have taken very, very seriously. Now, I want to emphasize, I don't believe we should be pursuing hypersonics just because the Russians and Chinese are. I think it's important we do it regardless. This is an important future military capability. But Russia and China are driving the timelines. The fact that they've already gone to deployment while we're still doing experiments and demonstrations tells us that we're in a race and we need to move as quickly as possible. And I think that's driving a lot of the investments that I talked about earlier. All right, question about importance of wind tunnels. Do we have enough? Simple answer, no, we don't have enough. As the Chinese were building new wind tunnels, we were shutting wind tunnels down. We need more wind tunnels. We are climbing all over each other right now in the United States, trying to get wind tunnel time. You saw that list of 70 programs. Many of them depend on wind tunnels, right? The fact that we don't have enough wind tunnel facilities is bad for many reasons, not the least of which is I do an experimental run in a wind tunnel. Something goes wrong. I didn't get my data. Tough luck. I don't get more time because someone's coming in after me. Or I do an experiment. I see something interesting. I want more time in the wind tunnel. Tough luck. You don't have a window to do it because someone else is coming in behind you. So our facilities are oversubscribed. I'll also say we have a problem with flight test, right? We've made it too difficult to do flight testing. I showed you a picture of the X-15 rocket plane from the 1960s. That thing flew 199 times. It was 3 different vehicles, but they flew 199 times throughout the 1960s. That was once every 18 days. We don't operate that way, and we really need to be moving into that direction. All right, let me scroll a little bit further down. Let's see. The Russians learn from live tests. Yes, they do. That's not a question. That's a statement. The Chinese do too. They have a big advantage with that. All right, let's keep going. What are the options for counter hypersonic weapons? I like that one a lot. There are a lot of options. All right, I said hypersonics are hard to stop. They're not impossible to stop. All right, there are several categories of things you can do. One is you hit a bullet with a bullet. You use a hypersonic weapon against a hypersonic weapon. Hard to do, but not impossible, especially at certain phases of flight. Second, you use the hypersonic weapon's energy against itself. Right? If I'm flying at high Mach number, almost anything that I hit, anything that I strike is going to destroy me. So a wall of metal, gun solutions, anything that can obstruct that vehicle, it might even be a cloud of dust possibly, will work against me. Directed energy, another possibility. Lasers, high-power microwaves, hitting sensors, hitting delicate components. And then finally, left of launch. If I can prevent them from ever launching that hypersonic system, then obviously I've defeated it. I might just do some approaches where I steal energy from the hypersonic weapon. Right? I force it to maneuver. I force it to bank and dive and turn, so it doesn't have enough energy to reach its target. I might not do a vehicle kill, but I can do a mission kill. And if I can do that, then I've effectively neutralized the weapon. All right, question. Once a hypersonic missile has been tested, how complicated is it? Is the reduction of the missile compared to other missiles? I love that question because there is a school of thought that says hypersonics will always be more complicated and more expensive than their lower speed counterparts. I don't believe that's true. Right? Think about a scramjet engine. It is a very, very simple configuration. It is an open duct channel. It's a hole in the front, it's a tube, it's got injectors for fuel, and it's got a nozzle. Manufacturing can be a little bit complicated. The materials that it's made out of can be complicated, so they have to be high temperature, but intrinsically, there isn't something that should be an order of magnitude more difficult about a hypersonic weapon as compared to a lower speed system. There is a typical mantra that hypersonic weapons are going to be $50 million, $100 million. I like to point out that somehow the Russians and Chinese have figured out how to do this at a moderate cost. One of the reasons that I'm a big fan of the air breathing solutions is I think that you can get those costs way, way down. They're probably going to be more expensive than their lower speed counterpart, but maybe a factor of 2, not an order of magnitude. All right, let's see, another question. What detection strategies can be used against hypersonics? I love that question because one of the other problems with hypersonics is that from a defense standpoint, they can be hard to detect. Now, on the one hand, they're hot, so you can see them in the infrared, so that's good. It makes them easier to detect. But on the other hand, by their very nature, they tend to be slender. These aerodynamic shapes have to be sharp, they have to be thin, and as a result, they don't present much of a cross-section. More importantly, hypersonic vehicles tend to fly at certain altitudes such that they're hard to see both from the ground and also from space. All right, so think about this. If I'm standing on the ground looking for an incoming weapon, the higher the weapon, the easier it is to see because the further over the horizon that I can see. Hypersonic weapons tend to operate at lower altitudes than, say, conventional ICBMs. So that makes them harder to see from the ground. Now, we also have space sensors that can detect weapons. And indeed, we can detect ICBMs, for example. The Missile Defense Agency depends on detection in space. But there I'm depending on the fact that I can look up into space against the dark background of space. If I'm looking for hypersonic weapons, and especially air breathers from space, I'm looking down. And that means I'm looking at a hot object against a hot background, the warm Earth. And so again, that complicates the detection. So bottom line, the altitude at which hypersonic weapons operates also makes them more difficult. It's that combination of speed, maneuverability, and altitude that makes them so survivable. By the way, I've been told that we can go over a few minutes, so if the audience will bear with us. If you need to drop off, I understand. If you want to stick around for a few minutes, please, you're entitled to do so. Let's see. What kind of maneuvering system? Let's see. Let me ask. If I'm an aircraft subcontractor, what kinds of subsystems go into these hypersonic systems? All right, phenomenal question also. Lots of subsystems, all right? Like any vehicle, it's got propulsion, it's got structures, it's got control. You need fuel management, all the classic systems of any aircraft. But what's especially complicated, the point that I made earlier, is how incredibly integrated all these components are, right? Anything I do to the engine is going to affect the aerodynamics. The structure is going to be driven by the heating requirements, the ability to survive, the requirements to survive the heat in a way that's really far more challenging than any other aerospace system that I know of. Let's see. Let's keep moving down. What kind of maneuvering did the Chinese hypersonic perform that was supposedly so impressive? Ooh, this is one of those examples of if I told you all the details, I'd have to figure out a way to kill everyone in the webinar, and that's not a good thing. It wouldn't help our audience in future webinars. Let me say, I think what I can say is this: the Chinese have indeed demonstrated lots of maneuverability, and that, of course, is an attribute, as I mentioned, of hypersonics. And it was enough maneuverability that it got all of our attention, and it showed us that the Chinese are thinking about these systems in a very sophisticated way, right? So they're not just thinking about getting places fast; they're thinking about how they would be unpredictable as they fly, and how they would complicate our attempts at defending against their hypersonic systems. All right, Here's one. For hypersonic defense, do you think the public will accept defensive systems on the CONUS coastline if they're necessary? All right, I'm going to weigh in on that one. I'm actually not as concerned about hypersonic systems that would be used against CONUS as I am about systems that would be used within theater. And I'm not making light of the importance of defending the homeland. Obviously, we need to defend CONUS, no question. But I think in terms of the threats that we face, I'll ask the question, what is the threat posed by a hypersonic weapon compared to existing weapons? So today, let's think about if the Russians were to launch their ICBMs at the United States. That would be a really, really bad day. Let's get that out front. That's a bad day for all of humanity. But let's suppose the Russians launch their ICBMs at us. All right. If you see an ICBM launched, an intercontinental ballistic missile, if you watch the initial stage of its launch, you've got a pretty good idea where it's going. It's ballistic by definition. It means its motion is governed by the laws of gravity. There can be some maneuvering of an ICBM, but you've got a pretty good idea of where it's going. So let's say we watch the Russians launch a missile. It's coming at us. It flies over the pole, and we see it's going towards New York, as an example. I'm from New York. I'll use that as my example. All right. How do we respond? Well, our Missile Defense Agency systems aren't designed to respond to a full-on Russian attack or a full-on Chinese attack. They're really designed to handle the onesies, twosies that can come from a rogue nation, like a North Korea or an Iran. So the bottom line is we really would have a hard time stopping that missile. So what are you going to do? You'd have 20 minutes of warning. So are you going to evacuate New York City in 20 minutes? We couldn't evacuate New Orleans in 10 hours when we knew there was a hurricane coming. But trying to evacuate New York City in 20 minutes, I hate to say it, and again, I got family in New York, but it's going to be a tough thing to do. All right, now let's contrast that. Let's say the Russians launch a hypersonic nuclear attack on us. The big difference is we'll see it launch and we will not know where it's going. We won't know if it's going to New York or Chicago or Philadelphia or Dubuque. So what? We couldn't evacuate. We couldn't really respond effectively when it was ballistic. How does that really change the equation? I'd argue it doesn't change the equation very much. So the things, again, that I'm worried about are weapons that actually do change the equation. And those are the hypersonic systems that can maneuver and bank and dive and glide and hit an aircraft carrier. The maneuvering hypersonic systems that can maneuver, bank, and glide and hit an airbase, crater our airfields. That can, the hypersonic systems where we see a submarine launch and an opponent can strike our submarine before it can get out of the way. Those are the ones, in my mind, that change the equation most effectively for an opponent and the ones that we need to be thinking about. And the flip side is, those are the applications, from our standpoint, what are the applications that we're interested in? Well, one is being able to reach very deep into an enemy territory with surgical strikes, surgical precision, right? We see a competitor that's doing something bad. Let's say, for example, a peer competitor has an anti-satellite system and they start taking out our assets on orbit. And we want to hit that system deep in territory. And today, the only option might be a limited nuclear strike, which is something we would be very unlikely to do. Hypersonics might give us an option to do that in a limited surgical way. Let's say, for example, we see a shoot and scoot approach. We've got a peer adversary that's shooting at us with an erectable system, shooting at us and then getting out of the way. Hypersonics would give us the ability to respond very, very quickly. So all those applications, I think, makes hypersonics important for us. Those applications would be different from what our peer competitors would do, but nonetheless, I think it's an important next phase for future combat. Let's see. Here's a question. Can trajectory of target be changed in mid-flight? It depends on the system, but in most cases, yes. And remember, hypersonics isn't being developed in a vacuum, no pun intended. Undoubtedly, we'll have smarter and smarter systems guiding our hypersonic capabilities. You could think about the marriage of artificial intelligence capabilities with hypersonics to enhance the maneuverability, to have cooperative operation of hypersonic systems, right? We already think in terms of swarms of attacking systems at low speed. You might do that at high speed as well to increase the effectiveness. I want to come back to one of the questions about defending against hypersonic systems. I would often have colleagues in the Pentagon say, yeah, we've got an approach that will defend against a hypersonic attack. And I'd always ask, well, okay, you can maybe defend against a single hypersonic weapon. Can you defend against 2, 4, 5, 6, a dozen? Can you defend against a swarm attack? And I actually think that's a direction that an adversary is likely to go, and probably a direction that we would be going as well. All right, let me go back and see if I've missed any questions. All right, here's a question. Does the air-breathing hypersonic weapons ionized trail make it easier to detect the vehicle? So actually, air-breathing vehicles tend to operate at the lower end of the hypersonic Mach number scale. So they actually tend to have very little ionization. It's the rocket boost flight systems that tend to be more likely to be ionized. That can have an impact on their detectability. I can't give details over this, but I can tell you it can indeed change their detectability. And in some cases, it can make them less detectable. In some cases, it can make them more detectable. So it really depends upon the configuration. I will tell you there tends to be a mantra that I'll come back to, that hypersonic vehicles are easy to detect. In many cases, it turns out they're not easy to detect, and that's the nature of their shapes. And also, you might be able to see the hypersonic vehicle, but it could be very hard to track it, and especially if it's maneuvering. All right, my technical team is giving me the high five sign. So I think we've gone through most of the list of questions. And again, I want to thank everyone for this little experiment in our one-on-one series. I just want to again offer, if you have any feedback about this series, about this seminar, if you want to tell us about topics you'd like to see us cover, please email us at eti@ndia.org. I also want to show you some of our upcoming events. May 26th, we have the legendary Dr. Paul Lapata, who is the former principal director for quantum science, doing a seminar on quantum science. Paul is one of the nation's great thinkers in quantum technology. He led our efforts in the Pentagon, and we're thrilled to have him doing this presentation. Then on June 9th, Justin Sanchez will be talking about biotechnology and why it's important for national defense. We've got on June 23rd, Dr. Zombre will be talking about microelectronics. July 21, Dr. Ian Taylor on blockchain 101. September 8th, Mark Neese, the executive director of the Directed Energy Professional Society, will talk about directed energy. For those of you who are interested in directed energy being used as a defense against hypersonics, there's your opportunity to learn even more about directed energy, lasers and high-powered microwaves and everything associated. And then finally, September 22nd, Quantum Computing 101 with Dr. Scott Fletcher, who's the Assistant Director for Science, Technology Assessments and Analytics at the GAO. And we will be adding more of these seminars as per your interest, as per your feedback, and as to everyone's availability. So with that, once again, let me thank you so much for your participation and your great questions, and I'll wish you a great rest of the day. Thanks a lot.